All right, so this is another recent article about model editing, a unified framework for model editing. This article in 2024. So we introduce a unifying framework that brings two leading locate and edit model editing techniques. These are very popular methods, architectures that I will describe in the future videos. So they are under a single conceptual umbrella in this paper, optimizing for the same goal, which we call the preservation memorization objective. ROM uses an equality constraint to perform one edit at a time, whereas MEMIT employs a more flexible least square constraint that allows for batched edits. Following preservation memorization objective, we present equality constraint mass model editing algorithm for transformers, or EMMET, a new batched memory editing algorithm that uses a closed form solution for the equality constraint version of the preservation memorization objective. EMMET is a batch version of ROM and is able to perform batched edits up to a batch size of 10,000 with very similar performance to MEMIT across multiple dimensions. So with EMMET, we unify and achieve symmetry within the locate and edit algorithm, allowing batched editing using both objectives. So we present a unifying conceptual framework and show that both methods optimize the same objective. So you see a representation of preservation memorization objective that we first find keys to preserve. Which keys do you want to preserve? And the second step is find a key value to be memorized. So we memorize this key and value. The edit fact is this one. The president of USA is John Cena. And the third step, you change W0 to W hat. As simple as this. So instead of W0, you have W hat. This is representation memorization. We call them very simple idea. But the success of model editing is measured using standard model editing metrics. For example, efficacy score indicates if an edit has been successfully made to a model. It is measured as a percentage of edits where probability of new fact is greater than the probability of old fact for a query prompt. The second measure is this paraphrase score, which represents the generalization ability of model under an edit. It is measured as the percentage of edits where this probability holds under paraphrases of the query prompt. The third measure is called neighborhood score, which represents locality. This is an important measure, locality of model editing. In other words, it measures if editing of a fact affects other facts stored inside a model. Because we don't want to change what has already been learned. And we don't want to affect other facts. Generalization entropy is another measure which represents the fluency of a model post-edit. So we have a pre-edit model, but with that additional addition, we come to another model. We call it post-edit. But as I said, we want the prediction of them to be the same for what you have trained for the pre-edit. But for some hard example in the post-edit, you want to make sure that the post-edit is fixing these bugs. So this is the architecture, the layer being edited by ROM, MEMIT, and EMMET. So all of them It's like all of these architecture. It's like you have an attention, then you have this W fully connected, double projection, and finally your representation. So the output of a single transformer layer for a general decoder only LLM can be written like this. And this attention is multi-head attention. This NL here is nonlinearity because we have multi-layer perceptron, and LN refers to layer normalization. So the idea is this: in ROM style, they used this objective model editing can be reformulated like this, that you minimize this optimization such that this memorization, key value, this relation holds. And key K0 is now a matrix. It's a matrix of keys. It's a matrix containing all vectors whose representation we want to preserve. So the solution for ROM can be written like this. We call this the preservation memorization objective. Same for MEMIT. So this paper it's a unified method. Same paper, but now we have the same W hat KE. We want to fix this because it's our constraint. This is our constraint. Now it is inside the model, and we want to also preserve this term. And we represent their target representations. So the solution of MEMIT, this solution is just this one, that we deliberately write the first term in both solution in a similar form. The first term in delta, this delta, represents the residual error of the new associations, of the new keys and values when evaluated on the old weights. So this residual, which is what is missing, is a vector in case of ROM, since we are only able to make singular edits. So R is a matrix for MEMIT, consisting of row of vectors corresponding to each edit in the batch. Edit distribution algorithm, the difference in objective is not the only difference between ROM and MEMIT. MEMIT also additionally distributes its edits into multiple layers, which has been one of the reasons for success of MEMIT at large-scale batch sizes. And the edit distribution algorithm is separate from the solution of the ROM and MEMIT objectives, so we can apply the edit distribution algorithm when using ROM as well as MEMIT without distributing the edits into multiple layers. But this paper is about EM MEMIT. So this paper asked this research question: can we perform batch editing under an equality constraint for memorization? So we provide a closed form solution for batch editing where memorization is done with equality constraints under the preservation memorization objective, and thus present a batched version of ROM, a method we call EMMET, which is equality constraint. And then the derivation is the same. And we additionally let K these represent key vectors for E facts we want to edit in the model in the same time. So we want to find new weights, W hat, these W hat, for weight matrix W0. Again, we have this constraint. So as can be seen, the preservation of the representation happens in the first term, whereas memorization of the new facts are forced using an equality constraint in the second term. The above equation is solved using Lagrangian multipliers. The Lagrangian for the above equation for multiple equality constraints requires a summation of Lagrange multipliers. So to solve this Lagrange, just take derivative with respect to W, and then what you get is this. So we set K0 transpose equal to C0, which is invertible. So the unknown matrix of Lagrange multipliers can be found using this constraint in the previous equation. And replacing the above equation gives us the update equation. So there are two important matrices that are being inverted. The first one is C0, which is defined identically in both algorithms, whereas D is only inverted in EM-MET. The matrix is a square matrix of dimensionality equal to the number of edits. So they began experimenting with the batch one, but this has some limitations. It does not address deeper structural limitations within models, such as edited models inadvertently simplifying existing errors or introducing new inaccuracies. And then the effectiveness of our method varies depending on the complexity of the method architecture and the nature of edited knowledge, as evidenced by our experiments. Despite having a theoretically stronger memorization objective, EM-MET is not able to outperform MEMIT, which also indicates that we might have reached a saturation point for model editing using naive implementation of preservation memorization objective, underscoring the fact that significant progress is yet to be made in understanding the edit distribution and its implication. Thus, while our work contributes to a deeper understanding of model behavior, it is essential to recognize and account for these limitations.